Hello, everyone. This is Group 1 presenting digital transmission in free space through a high-powered laser. Our mentors being Dr. Wei and Dr. Carr, our committee being Dr. Sahawin and Dr. Maddox and Dr. Eikenberry. Meet our team. Alexander Simmons, a photonics engineer. Curtis Kane, an electrical engineer. Ivan Huang, a photonics engineer. And Monica Castro-Suarez, a computer engineer.
The basis behind this project is long-distance communications, which was forever changed thanks to the electric telegraph in the 19th century and the laser and fiber optic cable in the 20th century. As digital signals are composed of ones and zeros, a laser can be modulated so that it can represent those ones and zeros as a series of pulses. And free space laser communications already exist, but only with satellites. And what this project will demonstrate is terrestrial free space laser communications. The goals and objectives for this project. So the basic goals are digital to optical modulation by developing a system with pulse-coded modulation and purchasing a laser with TTL capabilities. And the other basic goal is maximum signal reception by constructing an efficient optical system and selecting a photodiode that can accept 980 nanometers, which is infrared. Um, and then for the advanced goals, we will be implementing real-time decoding by developing a microcontroller-based system and integrating AI or machine learning capabilities. The other advanced goal is optimization of signal transmission by simulating efficient optical layouts and searching for different types of lenses and mirrors. And then for the stretch goals, we can um, we can turn this system into one designed for off-grid and emergency uses by introducing bidirectional capabilities and developing smaller form factor systems. And the other stretch goal is megabit transmission by finding a lower wavelength laser and integrating electro-optical components. And then for the engineering requirements, we would like for the system to have a decoding accuracy of greater than or equal to 95%, a data transfer rate of 500 kilobits per second to 1 megabit per second, power consumption of less than or equal to 5 watts, the optimal transmission distance between 50 to 100 feet, power efficiency of greater than or equal to 85% with less than or equal to 5% voltage ripple, interference immunity of greater than or equal to 40 decibel reduction in EMI. And then the minimum focus power at the optimal transmission distance we would like to achieve is greater than or equal to 5% of the original laser power.
Hello, my name is Alexander Simmons, and this is a brief overview of the optical parts used in the project. We have our laser at 980 nanometers, our beam expander using a positive meniscus lens, a focusing lens, photodiode, and a bandpass filter. We will go into more details for each component and design calculations for them in further slides. For our laser, we compare different laser types with parameters such as pulse duration and repetition rate, and we went with the TTL modulated laser diode because of its simplicity, affordability, adequate modulation speeds for free space optics, and compatibility with beam shaping optics at 980 nanometers. The higher end lasers such as femtosecond fiber were ruled out due to excessive cost and complexity not needed for mid-range data links The design calculation on the right shows power density for the TTL laser at 1 kilometer, showing it produces more than enough power per centimeter squared for our purposes. For the photodiode comparison, we compared different parameters such as responsivity, bandwidth, and internal gain over PN diode and PIN and avalanche photodiode. We chose the PIN photodiode due to its happy medium responsivity to cost ratio of 0.6 amps per watt at 980 nanometers, and its 30 megahertz bandwidth supporting pulse modulation, its lower dark current and noise, and its adequate speed for TTL modulated laser pulses at 100 kilohertz. The design calculation on the right shows our photocurrent signal with incident power and our signal to noise ratio with theoretical amplifier noise current. For our different expanding lenses, we compared different parameters such as beam expansion quality, various different aberrations, and transmission efficiency. We went with the positive meniscus lens because it had a lower divergence when compared to other lenses, the meniscus ones being 0.8 millirads versus greater than 1 millirad. Its spherical aberration was more manageable. It had a higher transmission and compact design when compared to others, and it had a less complexity and cost than the achromatic doublets. For the design calculation on the right, we show the beam divergence and the beam size with and without expansion, showing the different beam sizes over distances with and without the beam expander. For our focusing lens, we compared different parameters such as spot size, aberration correction, focal length, and numerical aperture. And we went with the aspheric lens because of its tighter focus, being less than 10 micrometers, matched the photodiode aperture and the distance we want between it. The numerical aperture of 0.55 enabled strong convergence from wide input beams. Its low aberration improved our accuracy and had an AR coating optimized for 980 nanometers. The achromatic lens we excluded due to unnecessary chromatic correction and added bulk cost. For our optical filter, we compared long, short, and bandpass filters with parameters such as central allowed wavelength and transmission efficiency. We went with the bandpass filter because it provided a 99% transmission at the laser wavelength. It blocked unwanted ambient light across visible and infrared, and enhanced signal-to-noise ratio under outdoor lighting conditions, and is more selective and efficient than short pass or long pass ultra. The next component comparison we will be doing is the methods of combining the beams that we're using. The main methods are polarizing beam combiner, wavelength division combiner, and non-polarizing beam splitter. The best method that we chose was the wavelength division combiner because when two different lasers are used at different wavelengths, especially for high efficiency applications such as telecommunication, it has a higher efficiency at 95 to 99%, meaning that there's minimal insertion loss, and it preserves almost all input power. And it has low crosstalk when combining the beams with minimal interference. It has broad wavelength range compatibility from 635 to 980 to 1550 nanometers, and it also has stable and low alignment sensitivity, which means it was designed with a relaxed angular tolerance between 2 to 5 millirads, making it easier to align and maintain over time. The next slide is our optical systems diagram. You can see starting up in the left-hand corner, the system begins with a microcontroller that modulates a 980 nanometer laser diode using a TTL signal. Then we have our red guiding laser hooked up to a switch to turn it on and off when needed. Then the beam is going through the beam expander, expanding and growing larger, using a meniscus lens to reduce divergence and maintain culmination over long distances, our alignment mirrors. Then after traveling through free space, our simulation distance was about 1 kilometer, which we simulated using at lower powers and other effects. The beam then passes through a 980 nanometer bandpass filter to block ambient light, and then a focusing lens then concentrates the beam onto the photodiode with fine adjustment mirror, which then converts the optical signal back into an electrical signal for decoding and display. For our beam propagation challenges, atmospheric effects of free space optics, the main takeaways are the key trade-offs of smaller beam diameters increasing divergence and reducing range efficiency, and without the culmination lens, the beam will spread over distances which reduces the intensity at the receiver. The long-range impacts over longer distances, 1 kilometer to 2 kilometers, are higher alignment sensitivity, reduced signal-to-noise ratio under turbulence, and limited beam range without optical correction. This is a brief example of atmospheric effect on beam divergence. You can see the wider cone of divergence seen at the left-hand side. expanding through the atmospheric turbulence in the lens system, and you can see how the arrows through the lens system are being diverted by these effects through the entire system. And these effects can be anything from heat, wind, or any sort of turbulence. These effects make it more difficult for the smaller beams to reach its target accurately, even through precise alignment, and cause the beam to wander, essentially. For larger beams, it is less affected, but it is instead resulting in a speckle pattern in the beam itself. To mitigate the constraints above atmospheric effects or beam divergence, the project implements a beam expander at the transmitter and a focusing lens at the receiver. For the beam expander to reduce divergence, we increase the initial diameter of the beam via the beam expander and culmination lens system. This system then reduces our divergence angle, preserves our beam intensity, reduces beam spread, and ensures adequate optical power reaching our detector. For the focusing lens at the detector, it then catches the expanded beam, focuses it into our fine adjustment mirror that we can then adjust into our photodiode head or detector, and it compensates for small adjustments error from its atmospheric effects since it's not a smaller beam going through our transmission distance. For our speckle pattern in large and small beams, the overall is smaller beam sizes, the speckle pattern is densest and easier to average with our photodiode. For our larger beam size, the speckle pattern is larger or expanded and more difficult to average with a single detector head because of hot spots in the speckle grain. For our design solution, the beam expander reduces divergence from atmospheric effects by making the beam size larger. The focusing lens then reconcentrates the expanded beam so the photodiode can average the incoming data. For our results, it should improve our signal to noise ratio, reduce our alignment sensitivity and beam divergence, and make it more easy and more reliable for averaging of our detection of our beam by the photodiode. This is a brief example slide showing the speckle pattern of expanded beam, and in section B you can see the hot spots in our beam in the beam itself. This is our main optical calculations and software used to test or evaluate our optical systems, which we will talk about more in the further slides.
Hello, everyone. My name is Monica. This is the engineering specifications for the software that I used. I changed from the last time. I switched from Arduino IDE to Code Composer due to its much more easier for the MSP430 that I'm using, especially since I'm working with a transmitter and a receiver. The performance is high and the experience is intermediate compared to the Arduino IDE, but after a while it became much easier to navigate my way around the software.
Hello, this is Curtis Kane, and this is the start of the hardware design. This slide shows an overview of our hardware pipeline. It starts with a microcontroller that converts written text from the laptop to binary data that will be used to toggle the laser in a subsequent manner so that zeros will represent when it is off and ones will represent when it is on. The laser beam then travels through an optical path composed of lenses and mirrors for beam shaping and collimation. At the receiving end, a photodiode captures the signal and the output current is converted to voltage using a transimpedance amplifier. Using the microcontroller's built-in analog-to-digital converter, the signal is then processed by the microcontroller and its output is then sent to the LCD to be displayed. Using Fusion 360, we developed a detailed 3D CAD model of the physical system, including the PCB container, condensed component layout, and light optical mounting. Two additional views are zoomed in to show how components like the PCB and photodiode are positioned for alignment. Creating this model helped guide physical prototyping by verifying mechanical fit, optical paths, and wire routing in advance. After comparing several microcontrollers, we ultimately chose the MSP430 G2553 for our main PCB due to its simplicity, low power consumption, and direct compatibility with the transmitter. While it has just 512 bytes of RAM and a 10-bit ADC, these specifications were sufficient for our signal processing needs, specifically reading the photodiode output and relaying binary values to LCD. The MSP430 also runs at 16 MHz, which offered enough speed for handling real-time sampling without overcomplicating the design. Additionally, its 1.8 to 3.6 volt operating range paired well with our voltage regulators and helped streamline our power system. Although other options like the ATmega 328P had more memory and peripheral options, the MSP430's straightforward architecture and lower power profile made it the better fit for our signal detection and decoding application. This schematic shows how we wired the MSP430 G2553 to support laser modulation, photodiode input, and LCD output. The inclusion of programming headers to reprogram the MCU aids in making the PCB easier to troubleshoot in the future, as we can now adjust the code on the fly if any parameters were to be changed. Power connections to both 5V and 3.3V rails are also included as part of the MCU design to power both the LCD header and the MCU itself. This clean layout will allow us to easily troubleshoot and test each stage of the system. The OPA 381 was our amplifier of choice for the photodiode to transimpedance amplifier signal chain. Since it is optimized for transimpedance applications, it has a very low input bias current of only 3 picoamps on average. Its 18 MHz gain bandwidth makes it ideal for detecting fast optical pulses with minimal signal degradation. And at around $1.80 per unit, it offers strong performance without breaking the budget. Here you can see our transimpedance amplifier circuit using the OPA 381. Instead of a single hardwired photodiode, we opted for a header to bring more adaptability to our overall circuit design. This header will allow us to swap the photodiode easily in direct response to any dramatic changes in wavelength of our input laser. With the photodiode wired into the header, the photodiode's current will enter the inverting input, and the output will provide a clean voltage signal proportional to light intensity. To power the system reliably, we implemented 2 boost regulators on daughter boards. We used the TPS 6132221A to generate 3.3 volts for the amplifier and the TPS 6133322A for 5 volts to power the microcontroller and LCD. These regulators helped ensure stable performance even as battery voltage dropped, which is critical during long testing sessions. This slide brings it all together, showing the complete system schematic. You can see the flow of signals from the photodiode and amplifier into the microcontroller, which then sends data to the LCD. It also shows programming pins and extra LEDs for debugging, an important feature that will save us time during development. During the prototyping phase, one of the main challenges we faced was related to timing synchronization between the transmitter and receiver. Initially, we used an ATmega microcontroller on the receiver side, but aligning its timing precisely with the MSP430 base transmitter proved difficult. The mismatch caused unreliable data reception and inconsistent signal decoding. After analyzing the issue, we decided to swap the ATmega for another MSP430 on the receiving end to match the transmitter. This change resolved most of our timing problems and simplified debugging since both microcontrollers now shared the same clock behavior and instruction timing.
Design flowchart. This system enables wireless data transmission using a high-power laser. Input data is encoded into binary by a light microcontroller and sent as light pulses via optical transmitter. A photodiode receiver captures the signal and converts it back into electrical data. A decoder reconstructs the original message, which is then displayed on an LCD. The software manages encoding, timing, error handling, and display formatting for reliable real-time communication. This is our general overview of the software design that we are using. Prototype and testing, the software section. For our final demo, we began by developing and testing the LCD and LED logic separately before integrating it into a full hardware system. We transitioned to using the MSP430 G2553 to better support the UART communication for user input through PuTTY and to simplify integration with our I2C LCD and laser control on our custom PCB. The goal of the system is to for the user to enter a word, for example, hello, using putty. The word is then displayed on the LCD. Each character is converted into binary expression, and the laser and LED blinks accordingly to the binary bit, where 1 triggers a blink and 0 leaves it off. What you are seeing today is the core transition logic in action. It serves as a major milestone towards the final integration and validation of our project. Problems encountered and solutions developed. Some of the major issues have been the syncing issues between transmitter and the receiver. The binary bit sent via laser is not properly aligned with the receiver end, which leads the laser to add extra bits or not even read the bit correctly. We came up with solutions where we would send 3 bursts of laser so that it would reset the receiver end. We are still working towards getting it to read it properly. We've had some success, but on some occasions we have not gotten it to read it fully. We've also run into the issue of the UART communication with putty not working as intended. We've kind of scratched that part of not letting the user input anything. We've just hard-coded everything from A through Z and just gone to the part where it's gonna just read 1 letter at a time.
The photodiode that we're using is the FDS 100 silicon photodiode from Thor Labs, and the critical aspect of the photodiode that we will be measuring is the responsivity, as it will determine how well the receiver will detect the laser signal. And from Thor Lab's specification sheet, the theoretical responsivity is 0.6 amps per watt at 980 nanometers. And then the measured responsivity is 0.585 amps per watt, which is not too far off. And for modeling the optical system, we're using Zmax, and the below diagram shows what our system looks like. And for the range test, we tested how far the 980 nanometer laser will travel at different distances, up to 100 feet. We were able to get to 100 feet, and the measured power is at least 7.9 milliwatts. For work distribution, Curtis's primary role will be PCB design and assembly, and his secondary role is embedded coding. Monica's primary role is embedded coding and software design. Her secondary role will be website design and management. Alexander's primary role will be optical design. His secondary roles are laser calibration and alignment and 3D modeling. And my primary role will be optoelectronics testing, and then my secondary roles are optical simulations and also 3D modeling. And then here is our budget, which consists of 3 IR laser diodes, 1 red laser diode, 1 photodiode, 1 LCD, 1 pack of LCD screens, a transimpedance amplifier, pack of microcontrollers, a batch of PCBs, power sources, and stainless steel rods, all totaling to $458.52.
1. Progress and plan for completion. Progress chart for senior design 2. This is the progress chart. Now that we are at the end of senior design 2, we're nearly completed with everything. The only thing we are struggling with is the embedded software, in which we hope to be done by demo day. Our plan for completion has been our go-to checkup on dates to make sure that we are on track with our deadlines and not late with assignments, and thankfully have not been late with any of them. Does anyone have any questions regarding our projects? If so, please let us know. Thank you for tuning in.